So in this video, I'd like to introduce a bit of a strange idea, but it's actually an important idea as we start to move into more complicated systems. And it's actually a connection between free body diagrams and those good old diagrams that you might remember from ModSim stock and flow diagrams. Um, and I introduced this with a certain amount of trepidation because it's often really confusing for people, but I think in some ways the stock and flow formalism is one that really helps you think pretty clearly about this idea of momentum flow and how you can think about systems where you don't just have forces, but you also have masses crossing system boundaries. So let's think about just a simple example first. So here's a simple example. We've got a block that is on a ramp, right? What's the free body diagram look like for this block? Well, if we do a sort of pure particle abstraction of it, we have gravity acting on the block, and we have a normal force that's acting on the block. Okay? So that's one way to sort of represent the idea that this object has forces acting on it, and that because the forces are acting on it, these forces taken together, the sum of the forces acting on the object, are going to tell me what the time rate of change of the momentum are. And since the object doesn't have a mass that's changing, that momentum is the mass times the velocity, so it will be the mass. Time rate of change of that will be the mass times the acceleration. Okay. Now there's another way we could sort of represent the same idea. We could, instead of drawing a free body diagram, we could look at this differential equation and we could think about, well, what does that differential equation mean from a stock and flow perspective? Well, from a stock and flow perspective, what this differential equation is saying is that the momentum of the system, which is a stock, right? So this block has some momentum p, okay? And that momentum is changing, and it's changing due to forces, right? In other words, force is a flow of momentum. And I will say that again, force is a flow of momentum. Force is the thing that causes momentum to change. If you look at the units of force, right, the units of force are newtons, which is kilograms times meters per second squared, right? If you look at the units of momentum, it's kilogram meters per second. So force has units of momentum per second, which you of course can also see by looking at the differential equation. The force is the time rate of change of the momentum. So I could also say, you know what, actually I've got two flows of momentum into this system, right? One of those flows is the normal force, right? And another one of those flows is the gravitational force. Okay? And I certainly could look at this diagram and say, yep, I can write a differential equation for that. The time rate of change of the momentum is plus n vector minus mg j hat, which is the same differential equation that I would write here. Okay. Now, why would I choose to draw it in this crazy way? Because this, in some ways, just seems so much more physical and seems like it makes so much more sense. The reason why I've chosen to draw it in this crazy way is this actually makes really clear the idea that what you are keeping track of is the momentum, and the question you have to ask is, what are the things that can cause momentum to change in a system? Okay? So one of the things, so if we ask that question, how can momentum change? Well, momentum is a conserved quantity. Which means not that it doesn't change, but instead it means that it only changes when there is something that causes it to change. And so the things that cause momentum to change are, one, interactions, which is to say forces, Okay? So when you apply a force to something, you cause the momentum. You can cause the momentum to change. And so in this particular case, you've got both gravity and the normal force acting on it. That's going to cause the momentum to change in this case. And the other thing that can cause momentum to change is if you actually have momentum crossing the system boundary. And I'll say momentum in particles. Okay? And so I'll give you an example of that. Let's imagine that you've got the Earth. That's the Earth. And we define this as being the system boundary. Okay? So everything outside of that dotted line is outside of the system. Everything inside the dotted line is inside the system. The Earth is moving at some velocity v. So if I think about what the momentum of this system is versus time, well, the momentum is in the I hat direction, and it's some value m sub e times v in the I hat direction, right? So it's a constant value, assuming that the Earth is, we're on a time scale where the Earth is not getting pulled by the sun significantly. So on a day-to-day basis, it's nominally constant. Yeah. Now let's imagine there's an asteroid that comes along. Well, what happens to this system when that asteroid crosses the system boundary? Well, the asteroid has some mass, m sub a, and it's got some velocity, v sub a. So depending on how you define your system boundary, you could say, what happens actually is that the momentum of the system changes. And the reason the momentum of the system changes is that this additional mass entered the system, which is carrying momentum. In other words, you had a particle cross the system boundary, and that particle was carrying momentum. And so at that point, when this asteroid crosses the system boundary, suddenly that momentum has to change, right? As a function of time, it has to change because now you've also had a mass change in the system. Okay? Same thing actually applies when you think about, say, a rocket flying. Right? With a rocket flying, the mass of the system is changing, and you actually have rocket fuel leaving the system, and that rocket fuel, when it's leaving the system, is carrying momentum, and so the momentum of the remaining rocket and fuel has to be changing as well. Okay, and this is why this sort of idea of particles crossing the system boundary is why, in some cases, really being more explicit about thinking about Stockholm flows for this and trying to think about what are the ways in which momentum can change ends up being kind of a powerful and useful idea.